Hello everyone. This is the first tutorial of a series on first year university physics. By myself, Professor N Kaloyerou. We'll begin with vectors. There'll be in two parts. Part one, I'll do part two in a separate video. We begin with vectors because they're essentially used throughout a first year university physics course, along with other basic mathematical concepts, algebra and such. But before proceeding, just a general note about the nature of these revision notes or summary notes. These are notes that I give to my students, tutorial group students, before we proceed to solve problems. They're intended to be brief and to contain the essential elements of each topic, the essential formulas and the essential concepts. If these are understood, many problems in physics can be solved. Before proceeding, two more things. One, just to introduce myself since this is the first tutorial. And secondly, I would just want to give you a strategy for problem solving. So let me first go on then to introduce myself. This is a little bit about myself. I'll leave you to read a little bit of my history. My name is Professor Nikos Kaloyerou. It's a Greek name. K is pronounced as a G. So, as I say, I will leave you to read this for yourselves. My research interests are foundations of quantum mechanics and quantum field theory. These are two of my main publications. These are more recent ones, but the ones that are relevant to you, these are a bit too advanced. But for you that you might be interested in, since you're doing labs, is I wrote a book in 2018 on basic concepts of data and error analysis with introductions to probability and statistics and to computer methods. The first chapters are very basic introductions to error analysis. I include a few detailed derivations which can be left out on first reading, but it's a book that might be useful for you when you're doing labs. One of my chapters is exclusively on probability and statistics. This is a standalone chapter which introduces probability and statistics. And this can be read alone and doesn't need to be read if you need just to learn what you need to do for your experiments. The very last chapter of the book is on computer methods. I basically solve one or two experiments using computers. And I did 4 different ways. One, I use the ordinary Excel worksheet, which really isn't very good. But I also solve it using 3 mathematical packages: Mathematica, Maple, and MATLAB. These are much more powerful tools. So I go through a couple of examples to show you how to use computers to analyze your experiments. Anyway, in case you're interested for your first year labs, you might want to look at this book. But let me just remind people how to approach solving problems. It's very important to start by drawing a diagram, even a very simple one. Some problems will need a complicated diagram. Other problems will need a simple diagram. But the thing about doing a diagram, it helps you to understand the question. So it's very important that you draw a diagram. The next thing is write down the given data, the data that's given to you in the question. By doing this, it gives you a hint as to which formulas you need to use. So in particular, you also look at what you're trying to find. So you write down the formulas that contain the given data and also the quantities that you want to find. In very simple problems, there may be only one formula, but generally speaking, you'll need more than one formula. But at least you'll be guided as to the number of formulas that might be relevant to your question. So you may write more than maybe a few formulas that contain the data and contain the quantities you want until you find the right combination to solve the problem. The general rule is answers should be given to the least accurate data in the question. So if your least accurate data is 2 significant figures, you should give your answer to 2 significant figures. If you have other data which is more accurate, 3 or 4 significant figures, you ignore that. You give your answer to the least accurate of the data in the question. When doing calculations though, always do the calculations one more significant figure than is required in the answer. Otherwise you'll propagate too many errors by the time you get to the final answer. So always calculate to one more significant figure than required in the answer. Now sometimes you have different parts of a question, A, B, C, D, etc. So you do a calculation in A, you give your answer rounded to whatever number of significant figures. Let me say 3 significant figures. Then you go on to part B and you use the results of part A. When you reuse results of an earlier part, you use the unrounded figure. So let's say you were calculating part A to 4 significant figures, gave your answer to 3 significant figures. Part B, you need to use the result from part A, so you use the 4 significant figures, the unrounded number. The last point to remember is convert to base SI units. So convert your data to base SI units. That way, you'll get your answer in base SI units. You can get the right answer by not doing this, but you often may not interpret the answer very well, and also you may even get the wrong answer. So it really is better. It's a bit more work, but it's worth converting to base SI units. When we're just doing normal mechanical calculations, the base SI units are kilograms, meters, and seconds. Obviously, when we come to other areas, electromagnetism, for example, you'll need units for electricity and magnetism, and so on. But while we're doing mechanics, the base SI units you will need is kilograms, meters, and seconds. Now let me go to the whiteboard before we start and make sure that everybody does know significant figures and decimal places. Again, this is revision. I'm aware of the fact that you should have done this in your lectures and even at school. So let me go to the whiteboard and let's look at significant figures first. Supposing I want to round off to say 3 significant figures. I'll abbreviate 3 significant figures as SF. Now I want my answer to 3 significant figures, so I calculate to 4 significant figures. And by the way, in my solutions for these tutorials, I'm going to ignore what's in the question and always do my calculations to 4 significant figures and give my answer to 3 significant figures. So let's look at significant figures then. 3, 4, 6, 7, 8. Here we have 1, 2, 3, 4, 5 significant figures. Now let me say I want to round off my answer to 3 significant figures. This becomes 34.7. If I do another one, again this is in 1, 2, 3, 4, 5 significant figures. I want my answer to 3 significant figures. So it becomes this. Now the rule is this. If I want my answer to 3 significant figures, I look at the 4th figure. If it's 5 or above, I add 1. Similarly here, I look at my the fourth significant figure, and if it's 4 or less, I leave the third significant figure unchanged. So this is the rule. 5 or above, I add 1. 4 or below, I leave unchanged. So those are significant figures. One other thing though, when we're calculating to 4 significant figures, and you punch onto your calculator, so quite often your calculator will give you quite a few significant figures. It's not strictly necessary, since you're going to round off to 3 significant figures, it's not strictly necessary to do this. But I've noticed a lot of students in the past like doing it. So when they do the calculation, they see this on the calculator, and they're doing the calculation to 4 significant figures. So they write this, but now they look at the 5th significant figure, and if it's 5 or above, they round off. So they proceed with the calculation with 4 significant figures. It isn't strictly necessary to do this. You can just look at your calculator and just look at the first 4 significant figures, since you're going to round off at the end to 3 significant figures. However, it is slightly better to do what many students like doing, which is to look at the 5th significant figure. This is assuming you're calculating to 4 significant figures and giving your answer to 3. As I said, strictly speaking, you should look at the least accurate of your data in the question and give your answer to that number of significant figures. But as I say, in my tutorials, I prefer to work to calculate to 4 significant figures and give my answer to 3 significant figures. This extra bit of accuracy helps me to see when answers are right or wrong, and this is why I prefer to do it this way. Now let's also look at decimal places. What is the difference between significant figures and decimal places? Now supposing I want my answer to 2 decimal places. Let's look at some numbers. 78.234 5 and 78.237.6. Okay, so I want my answer to 2 decimal places. So I look at the third decimal place. If it's 4 or less, I leave this unchanged. So this will be 78.23 to 2 decimal places. Now let's look at this number. Again, I look at my third decimal place. If it's 5 or above, then I increase this by 1, or I add 1. So this becomes 78.24 to 2 decimal places. So just as with significant figures, if your next number after the one you want to correct is 4 or less, you leave it unchanged. If it's 5 or above, you add 1. Okay? Now suppose we have a situation like this. We have a number 0340, and again I want my answer to 2 decimal places. Here what I do is I include the zeros. Even though they are 0, I still include them, because this indicates that I have rounded to 2 decimal places. And again, if it turns out that this is 5 or above, then I get 78.01 to 2 decimal places. Before leaving decimal places and significant figures, I want to finish up. Let me clear this. This is a mistake I've seen students do a number of times. So I want us to consider these numbers. Now we want to round off to 3 significant figures. This is a decimal point. I'll do the same number, but I'll write it as a whole number. In both cases, I want my answer to 3 significant figures. So here, I look at my 4th significant figure. It's a 3, so the 2 stays unchanged. So I get 78.2 to 3 significant figures. Okay, this is fine. Now let's come to this one. What I've seen students do when they're rounding off, they look at the 4th significant figure, leave this unchanged, and then they write 782. I think you can see immediately that this is completely wrong. It's wrong because we have left out the units and the tens columns. When we're dealing with whole numbers, we have to take account of the unit, tens, hundreds, thousands, etc. So if I leave out these 2, I change the number completely. Imagine these are kwacha. This is 78,234 kwacha. This is 782 kwacha. So you've lost an awful lot of money. So when rounding off with whole numbers, you must keep the units, tens, positions by adding zeros. So this is, in whole numbers, this is my answer to 3 significant figures. Do not leave out, chop off the units and tens columns. Here, when I leave the 3 and the 4 out, it doesn't change the magnitude of the number. Okay, keep this in mind when you're rounding off in your tutorial questions. Okay, I'll stop there. Alright, I think now we're ready to go to our very first tutorial, vectors. Now let me just change, I like to use the arrow as my pointer. Okay, let's start with what most of you probably know from your lectures. By the way, these summary notes that I'm giving you are not meant to replace your lectures. They are literally summary notes. Vectors is the only one that I do in perhaps a lot of detail. But for the rest of the tutorials, my notes are just summary notes. So let's start with what you probably all know. A vector is a quantity which has both magnitude and direction. Examples: displacement, velocity, acceleration, force, etc. A scalar is a quantity which has a magnitude but no direction. Examples are temperature, distance, speed, mass, density. Again, it's many other examples that you'll come across in your course in physics. Now, notation to represent a vector. You can either do a curly line under the symbol to represent a vector, or you can do an arrow on the top of the symbol. In this particular course, I'll use the arrow over the top of a letter to represent a vector. A vector is represented, we'll begin with geometric representation of vectors. We'll come to the mathematics later. But let's just picture vectors first. A vector is represented by a line whose length indicates its magnitude, with an arrow to indicate its direction. It is often convenient to represent vectors with respect to Cartesian coordinate axes, either in 2 dimensions or 3 dimensions, 3D for short and 2D for short. So I'll be using this shorthand for later in my notes. But we'll mostly be concerned with 2-dimensional vectors. It's quite difficult to picture 3-dimensional ones, though mathematically it's just as easy to treat 3-dimensional vectors as it is 2-dimensional vectors. Vectors with the same magnitude and direction are considered equal, no matter where on the xy plane they are drawn. Position vectors, these specify the position of an object. I think my spelling went a bit astray there. It should be specifies the position of an object. The tail of a position vector is always tied to the origin of the coordinate system. Let me go to the whiteboard just to emphasize what I have just said. So it's sometimes convenient for us to use a Cartesian coordinate system, the x-axis and the y-axis. Now I can draw a vector anywhere on the xy plane. Call this vector A. Now if I draw the vector elsewhere, it has the same magnitude and the same direction. In this case, the two vectors are equal. In other words, it doesn't matter where on the xy plane I draw it. I can draw the vector here. If this has the same magnitude and the same direction as A, my drawing of course is not perfect, then A equals B equals C. All the vectors are equal. While I'm on the whiteboard, I might draw you a three-dimensional vector, or how to represent it on the coordinate axes. It is always more difficult to picture or to draw three-dimensional vectors, but one way, there are two ways you can do it. One way is if I draw a box. Oops, let's do that a bit better. My box is not very great. Then I can draw my vector from the origin, from one corner of the box to the other corner of the box. This represents my 3D vector A, and then the sides of the vector represent its components. I'll come to that later. For now, it's just a way of showing you how to draw a three-dimensional vector. This is X, Y, and Z. This, by the way, is a right-handed set. Which means you obtain the axis by the right-hand rule. Flatten your hand, point your fingers. Well, I can't draw. I'm going to draw a very bad hand. This is a hand pointing in this direction. If you curl your fingers towards Y, your thumb will point in the Z direction. I'm not an artist, so my drawing is not fantastic. So flatten your right hand, point it in the direction of the x-axis, curl your fingers towards the y-axis, then your thumb will point in the z-axis. If you do this with a left hand, you'll end up with a coordinate system which is a left-hand set. Let's go back to my notes. Geometric addition and subtraction. If I take two vectors and I want to add them, I can write it mathematically in this way. This is not an algebraic equation. This is a vector equation. I'll deal more with the mathematics of this later. And I'll show you what this represents later. But for now, geometrically, all you do to add vectors is you place them head to tail. So I start with the A, draw my A, then I put the tail of B on A, and it takes me from the start position to the finish position. The resultant vector is a single vector that takes me from the same start position to the same finish position and in the same direction. So if you imagine walking from start point, follow the vector A, then follow the vector B, we end up here. The resultant is the vector which takes you straight from the start position to the end position. So we walk along here to get to the end. So the addition rule then, to add vectors, place them head to tail. The sum of vectors R is called the resultant. It is the single vector from the start position to the end position and points towards, I've written this twice, and points towards the end position. Cancel this bit. And any number of vectors can be added together by placing them head to tail. This is my vector equation, and this is my graphical representation. I might do this on the whiteboard for you. So let me take a vector A and another vector B. It's supposed to be, I want it to be horizontal to make things easier. The horizontal vector is a bit more difficult to draw. Now to add them, I take the vector A, I take the vector B, and I place the tail of the vector at the head of, on the head of A. So I go from my start position to my finish position, and my resultant is a single vector which takes me from the same starting point to the same finishing point. If I imagine myself walking, I walk from here to here, then I walk from here to here. So my arrow points in the direction always towards the end point. So this is my resultant. Now I can write this vector equation like this. I'll show you what this equation means in terms of components when we do that later. But for now, just focus on the geometric part. Again, if I take another vector C, perhaps a vector D, I can put all these vectors together. Let me try and see if I've got enough room. This is my A. All vectors place head to tail. My vector B, my vector C, and my vector D. So the resultant, if you imagine walking, we follow the direction of the vectors, so we walk from here to here to here to here, and we end up at the finish position there. The resultant, as always, is a single vector that takes you from the start position to the finish position and walking in the same direction, so you go from start to finish. So the resultant always points towards the finish point. And this can be written as A plus B plus C plus D. This is my D there. This is equal to my resultant. Okay, back to my notes. Oh yes, I'll do this on the, forget this, this is just, was supposed to be rubbed out. I'll do this on the board for you, but notice that you can add vectors in any order. You can start with A, and then, here we go. Start with A and add B, or start with B and add A. So you either put the tail of B on the head of A, or the tail of A on the head of B. You get the same result. And you can see this because the resultant R here is the diagonal of a parallelogram with sides A and B. So you can see the order of addition doesn't matter. The next thing is the subtraction of vectors. Now, the best way to think of subtraction of vectors is to think of adding the reverse of the second vector. So if we have two vectors, A and B, A minus B can be thought of as the addition of the reverse of B. So here I reverse B, and I add the reverse of B onto A. So this is my A, so it's head to tail again of the reverse of vector B. The resultant is from the start position to the finish position. Again, let me go to the whiteboard. So let's have a look at the order. A plus B equals B plus A. So if I take the vector, let me say this is vector A, this is vector B. So vector A, let me draw B a little bit longer. Where is it? The eraser is what I want. It's my vector B. The resultant, as we have said, is from there to there. Now if I do it the other way around, we see that it's two sides of the same parallelogram with the resultant R as a diagonal. Now subtracting vectors, let me take the same two vectors A and B, but this time I subtract B from A. And as I say, the best way to think of subtracting vectors is the addition of the negative of the second vector. The negative means the magnitude stays the same, but the direction is in the opposite direction. Notice the magnitudes do not change, just the direction is opposite. So in this case, if I start with A, remember the rule for addition is to put them head to tail. So I take my negative of B, place it head to tail. It's supposed to be horizontal. This is my minus B, and my resultant is going to be, this angle is going to be difficult to draw. You can see the resultants are different. Of course, reversing this will not give me the same answer. Maybe we can see that. Let me try the other way around. Let's see what happens if you try B minus A equals R. Let's see what this one looks like. This time I take B and I take minus A. It's supposed to be the same direction, just not very well drawn. So if I take B, minus A is now down this way. This is the start position. And my finish position. Notice I've put them head to tail. You can see the R is now in the opposite direction. The magnitude, however, is the same. Let's go back. Go back to my notes. Mathematics of addition and subtraction of vectors. For right-angled triangles, trigonometry is used, i.e. sines, cosines, and tangents. I won't do any examples here. We'll be doing a lot of examples in the various tutorials, so I will leave examples of this when we come to tutorials. For triangles that are not right-angled, the sine and cosine rules are used. You probably know these from your school days. However, Calculations with vectors are much easier in terms of components of vectors. We will consider components after the next two sections. I'm going to pause here from vectors and just go through. This is really his revision. It's things that you should know from before. The definitions of tangent, cosine, and sine. If we consider a right angled triangle, hypotenuse H, opposite O, adjacent A. Definitions are the same if I write theta here. It makes no difference. It's just that I will reverse the positions of the opposite and the adjacent. Theta, you can see, is always going to be less than 90. And this is a right angle there. Now, with respect to this triangle, we have tangent is opposite over adjacent. Cosine of theta is the adjacent over the hypotenuse. Sine of theta is the opposite over the hypotenuse. And I think you all know this mnemonic for remembering. SOHCAHTOA. Sine opposite over hypotenuse. Cosine adjacent over hypotenuse. Tangent opposite over adjacent. Now there's a more general definition of sine, cosine, and tangent. In terms of a vector that's tied to the origin and can rotate full circle. So consider a vector R with its tail tied to the origin, which can rotate full circle with magnitude the radius r of the circle. The angle theta is measured from the positive x-axis counterclockwise, or anti-clockwise if you like. Whenever we use Cartesian coordinates in 2 dimensions, we always measure the angle relative to the positive axis going counterclockwise. X and y are the projections of the vector on the x and y axes, and notice that x and y can be positive or negative. As you can see, you project r onto the x-axis, so here we have x. This is in the positive direction, so x is positive. Projection onto the y-axis is y, from here to here. Again, this is on the positive y-axis, so this is positive. If you have the vector in this position though, the y projects onto the positive y-axis and hence is positive, whereas the r projects onto the x-axis on the negative side, so we have minus x. So the x and y projections can be positive or negative depending on which quadrant. Here, with this for the vector in this position, we have both minus x and minus y. In this position, we have plus x and minus y. So if you notice that, we can then define generally tan theta is y over x, opposite over adjacent, cos theta is x over r, adjacent over hypotenuse, sine theta is y over r, opposite over hypotenuse. Before, with reference to the right angle triangle, theta was always less than 90 degrees. But now theta can have any value between 0 and 360 degrees. So this means that depending on the quadrant, tan theta, cos theta, or sine theta may be positive or negative. The way to remember what the signs are is by this mnemonic cast. One thing to point out before I explain cast a bit more. When you feed in the angle as measured from the positive x-axis counterclockwise, the cosine or the sine theta will come out positive or negative depending on how big the angle is. So if the angle lies in this quadrant between 0 and 90 degrees, all of them are positive. And then for this, in these quadrants, then we remember it by cast. And it goes like this. Draw a circle, divide up into quadrants, first quadrant, second quadrant, third quadrant, fourth quadrant. Start and cast counterclockwise. Quad A, this is sine, cosine and tangent are positive. The quad S, the second quadrant, sine is positive, tangent and cosine are negative. Quad T, tangent is positive, sine and cosine are negative. Quad C, cosine is positive, tangent and sine are negative. So this tells you which ones are positive. All are positive, sine is positive, tan is positive, cosine is positive. Now I'll just mention the sine and cosine rules, and we're not really going to use them because we're going to prefer to do our calculations in a very much more convenient component form, to which we will come. The sine rule, if we look at a general triangle and of sides A, B, and C, now the angle opposite A is alpha, the angle opposite side B is beta, and the angle opposite side C is gamma. Keeping this in mind, my sine rule is A over sine alpha, B over sine beta, C over sine gamma. My cosine rule, it's very like Pythagoras theorem, but it applies to all three sides, except we have this extra term that we subtract. So A squared equals B squared plus C squared minus BC cos alpha. Notice that alpha is the angle opposite A. And the vectors that we add are also the vectors that we multiply cos alpha by. Similarly here, B squared, alpha squared plus C squared, this is AC. So if you see the pattern, it's easy to remember. But always remember this is a minus sign that comes here. I will leave the sine and cosine rules just as I mentioned. We will not be using it. So this is a good place to stop. So we'll continue with the next tutorial, representation of vectors in terms of components. So let me say bye-bye for now until the next tutorial. Okay, bye-bye.